Right, guys, people are starting to join in. As they join in, I'll just do a quick review of what we studied last class. So, oh, what the hell is this? Oh, yes, it's the drawing. Oh, this is from last class also. Right. So, yes, we talked about the concept of projectile motion. So, projectile motion is basically when you throw something. Basically, we had different types of examples of what projectile motion is. Therefore, we talked about how if you throw an object, the only force acting on it is weight, which are the red arrows here. And that's why the only acceleration we have is downwards, which is constant and proportional to the weight. And we proved that using a few equations that F is equal to ma, so the acceleration is basically uniform. And then we even showed the motion on a velocity time graph. It was a gradient, constant gradient graph, which proves what? That the velocity is changing at a uniform rate, and the gradient of this graph is minus 9.81. And other than that, so what else have we studied? Oh yes, and we did mention that at the highest point the velocity is 0, and we can see that on the graph here at point B. Other than that, we talked about how if all of this was happening on a train, and if the train was moving, then to a stationary observer, he wouldn't see the ball going up and down, he would see it moving along a parabolic path. And then we studied about how we have something, if you throw an object along the path of a parabolic path, then we can split it into two components, a vertical component and a horizontal component. So if this angle is theta, and if this value is v, then this is going to be v cos theta, this is going to be v sin theta, based on the trigonometry that we actually went through previously, right? So we talked about this, and then we also talked about a very important thing, that throughout the entire flight, there's only one constant vertical acceleration. So we have, when this moves, you have uniform acceleration, but you have constant velocity horizontally. Vertical uniform acceleration and constant velocity horizontally. Why? Because we have a uniform constant force vertically and we have no force horizontally. So basically all of this proved that when we have projectile motion, these are the things that we can follow very easily. And we also talked a little bit about Newton's second law, which states that the rate, number 1, of change of momentum, number 2, is equal to, number 3, the resultant force, number 4, and the change in momentum is in the direction of the force. Right, so these are the stuff that we studied last class. So I guess we can continue from here. Now we're going to go a little intense with the maths, because there's a lot of equations and stuff that you have to be aware of. So the first thing that we're going to do is we're going to draw that projectile motion path again. Okay, so I'm going to take a scale this time. And there we go. So this is, say, the ground over which it's going to go. And I can also draw, say, the initial angle. So say this is the initial angle. So notice how I'm going to draw this. Sometimes they give this much and then they're going to ask you to draw the rest of it. So if I was to draw this path, what would it look like? It's going to look like this. Oh man, that was a nice parabola. Check this out.
That's pretty good.
Yeah, I know. It's so cool. So basically, realize how it's just a tangent here and it never exceeds this point. There's a lot of mistakes that students draw. If a question starts like this, sometimes they draw this and then like this. Sometimes they draw something like this. I don't know. But these are all wrong. The correct way of drawing it is basically like this. All right. And then moving on. So we can say this is theta. And we can say this is a velocity v. So the component here is v cos theta. And the component vertically is v sin theta. And as we established on the previous papers, what we established in the previous papers was that v sin theta is going to be affected by g. V cos theta is not going to be affected by g. Why? Because g acts perpendicularly to v cos theta and parallel to v sin theta. So what I'm going to do now is I'm going to do this really important thing. I need you guys to pay a lot of attention to what I'm about to do. So I will use two different colors to represent two different paths of motion. All right? So I'm going to use red to show everything vertical. All right? So red is vertical. I'm going to use blue to represent horizontal. All right? So that basically means v cos theta is a horizontal component. And v sin theta, v sin theta is a vertical component. That's pretty obvious. The next thing that you need to be aware of is that acceleration is going to act vertically, g. So that's why I wrote it in red. So say I want to find the velocity at the highest point, the vertical velocity at the highest point. So this velocity here is going to be 0 meters per second. That's why it stopped at the highest point, right? So the vertical velocity here is 0, but the horizontal velocity is still stuck at here at v cos theta. All right? So moving on. If this is 0 meters per second, I can actually create an equation to find the time required to reach the highest point. What would that equation look like? It's going to be, if I use the equation v is equal to u plus at. Notice how I'm using a red pen because this equation relates to the vertical values. So v is our final velocity vertically, which is 0 meters per second. Our initial vertical velocity is v sine theta. Plus a is g. In this case, we can write minus g, because downwards can be considered to be negative. So basically it's going to become minus g into t, right? So now we have all of these, so we can write an expression for t itself. So, all right, what I'm going to do is I'm going to use a special color for t. Maqsadul, can you tell me why I'm going to use a special color for t and not red or blue? Okay, if you have the answer, don't say it. Let's see if anyone in the comments can say it. Can anyone tell me why I'm going to write t in green? So this becomes t is equal to is minus v sine theta by minus g. So v sine theta by g. Anyone in the comments? If anyone can come up with it, please tell me. But t is written in green, you might notice. Right, so this is basically the time required to reach the highest point, and we're saying this time is time t. And again, for it to go from the highest point back down here, assuming there's no air resistance or anything, it will hit the ground again back at v sine theta. But there's going to be a minus because now it's moving downwards. All right, assuming that if this was v sine theta and this was 0 and this is minus v sine theta, then this is also going to be t. So yes, the total time of flight is going to be this t plus this t. So the total time, if I represent that with a capital T, is going to be equal to 2t. I'm seeing that in the comments, 2t. Mirror Sharif, good job. So that's basically the idea behind t. But it doesn't explain why it's green. Let's see. Because it's same for both vertical and horizontal velocity. Samin Saba! Congratulations! You won today's award. Yeah, you made it to today's page. Okay, congratulations, Samin Sabah. Like, you should screenshot this. Like, I'll put a little heart here. Not too big, all right? Just a small one. That's a nice little heart, isn't it?
That's pretty.
That's pretty. So the thing is that, yes, as Samin Sabah has very brilliantly mentioned, the t values are the same. And the t values, that's not why it's green. The reason it's green is because the time required for it to go to the highest point and then come back down again is also the time that it requires to travel the horizontal distance from here to here, like this. So up to this and back down to this, and this. These two values are the same. So yes, that's why t is a green color. Oh, someone feels jelly. Oh man. All right. So now that we figured out that the total time of flight is 2t, we can put that into the equation also. So the total time of flight becomes this final super green equation, 2v sine theta by g is equal to t. Now, coming back to our horizontal component, if you want to find out the horizontal distance covered, we actually call it a specific thing. It's called range. So if you want to find out the range of the object, so what do you do or how do you find it? It's very simple. You're going to use the equation that distance covered is equal to speed into time. So range is equal to v cos theta into, I'll use green here again, 2v sine theta by g. And then it's going to turn into a blue equation because it's purely horizontal now. It becomes v square 2 sine theta cos theta by g. So those of you who have ADMATs, I will mention a little bit of ADMATs here. Maksud, do you think you know what's the at mass I'm going to mention right now?
I don't know.
You don't know? 2 sine theta cos theta
10
is equivalent to, oops, it's supposed to be 3. Equivalent to, you don't know this one? Sine 2 theta.
Sine 2 theta, I know that.
You knew it? Seems like you suck at maths, man.
Just, yeah.
That's it. So that basically means I can write the whole sine 2 theta, 2 sine theta cos theta as sine 2 theta. So that means this equation will change a little bit, and it's going to become, this equation is going to become v square sine 2 theta by g. That's the range. Right? So this is an equation we can use for range. An interesting thing that this equation says is that for any given value of v, the highest value of the range is going to be when theta is 45. Because when it's 45, that's when sine 2 theta is 90. And the highest value of that is going to be how much? 1 plus 1. So v squared by g is equal to the maximum range that you're going to get. So now let's try drawing a couple of these parts. By the way, Samin Saba, here's your thing again. Congratulations, you won today something, right? We should make that a post, right?
Yeah.
Like, you know, congratulations to smartest student of the day, Samin Saba. Smartest student of the day. That's a thing. We should make it a thing. Legit. We
It
should
is a
make it.
thing.
Yeah, I know.
Thing now.
Okay, going on. Ki eshob P3 trigonometry lage na, guys. So anyway, now the colors don't represent components anymore. I'm just drawing stuff. So if you throw something at a 45-degree angle, basically that means it should fall onto a point here, right? So what's going to happen if I increase the angle? If I increase the angle, it's going to go like this. Even further, it's going to look like this. Even further, it's going to look like this. Have you seen those cricket matches? Just ye kore? And you see it going and in your brain you're already done the maths.
Yeah.
And you know that, like, you know,
Yeah.
he out. And why? Because like it's not going. And niche dekh one of those Indian cricket players বসে আছে একদম এরকম করে ক্যাচ করার জন্য পপ করে ক্যাচ করে বাংলাদেশি ক্রিকেট প্লেয়ার হলে, like, you know, sometimes they miss it sadly. But yeah, I don't want to try to single out Bangladeshi cricket players. Yeah, that's just something human, like, you know. But yes, support Bangladesh. So, and what happens if the angle is less than 45? Let's use another color for that. Let's use pink. We haven't used pink. So what would that look like? It's going to be less, all right? It's going to be less. So you get maximum range at 45 degrees. So what happens as you increase the range? As you increase the angle, as theta increases, if you look at the maths, if theta increases, then the value of v sine theta will increase. So that means it goes higher up at a faster speed. However, as theta increases again, the value of v cos theta decreases. So that means the vertical component constantly increases. And if v sine theta increases, based on one of the equations that we got, basically the equation for t was 2v sine theta by g. So the value of t will increase. So the time of flight increases as you throw it steeper and steeper. However, the horizontal velocity with which it travels decreases as you make it more steeper. So you need to find a balance between the two. And the balance is nicely shown by the equation that we just came up with a few moments ago, that r is equal to b square sine 2 theta by g. So this equation shows that the best balance is when you get a 45-degree angle. Right, so yes, that's most of the stuff about projectile motion. There's one or two other points that I would have to mention. Oops, this is moving a little bit. Okay, one or two other points that I must mention. One of the points I'm going to mention is when it comes to parabolic motion. When it comes to parabolic motion, here all of the energy is kinetic. V, say the velocity is v, and the ke is e. GPE is 0 at the high, and say this is theta. At the highest point, the kinetic energy, so the velocity is going to be v cos theta only. Why? Because the vertical component is 0 at this point. So the kinetic energy is going to be basically half m v cos theta square, right? So that's basically how we're going to find the kinetic energy. And then it turns, ignoring air resistance again, at this point all of the energy is kinetic energy. Here you could say GPE This is basically the KE. And the GPE is equal to E minus half mv cos theta squared. So they asked this question, like, for example, if this is 45 degrees, then how much is the kinetic energy in terms of E? If it's 60 degrees, then how much is the energy in terms of E? So basically what you have to do is stuff like, if the velocity is V here, then this is going to end up being V cos 45. And if you do the maths for that, Maxwell, what was cos 45 again?
1.
What?
Half.
Half.
Yeah.
All right. Are you sure about that?
Yes.
Are you sure about
I
that?
am.
Are you really sure about that?
100%.
All right, fine. So if you square this, it's going to become 1 by 4 v square, right? The kinetic energy. Are you sure about this?
I am.
Or is it 1 by root 2?
Oh, are you not sure?
Are you sure?
I am sure.
All right. All right. So basically that means that the energy here, the kinetic energy, is basically 1/4 of E, because half mv squared. And if it's 60 degrees, then according to Maxwell, it's going to be 1 by root 2, right? 60 degrees. Is it on radian?
It's cos 60s.
Oh my God, Maxwell.
I thought you were sure. And you're
Yeah,
guessing.
sure. Yeah, sure, man. So cos 45 is 1 by root 2.
Yeah.
Yeah, there you go. So cos 45 is going to be 1 by root 2. Sorry, guys. That was Maxwell trying to mess me up, sorry. Yeah, testing me to the point where I teach wrong stuff. Oh, look, I tested you as teacher. So yes, see, 45 cos 45 root 2 by 2. Ahmed Jubair, half of it. Good job, guys. Bad job, Maxwell. Bad Maxwell. So basically, 1 by root 2. So the energy, the kinetic energy is going to be half E. At the highest point, it's going to be half E when the kinetic energy, when the angle is 45 degrees. So when the angle is 60 degrees, what's going to happen is the value is going to become half. So if you square that, half mv squared, kinetic energy, that's going to be 1 by 4 v squared. So the kinetic energy at 60 degrees is going to be 1/4. So yes, let me just write that again here, really short. So if 45 degrees, then Ke at max is half E, where E is the initial energy. And at 60 degrees, Ke at max is 1 by 4E. So basically, what's the GPE then? If the K is half at max, then the GPE is going to be half E. And here the GPE is going to be 3 by 4E, which makes sense because this is higher up, right? So basically you have more energy. What else? So these are the basics of projectile motion, but yeah, you need to practice some sums.